Okay, these are going to be some example problems of kinematics. These will be the same examples that I did in class today. So you'll have the text of the questions you can add to, or if there's anything that you missed with the explanation in class, this is what you have. So the first thing we're going to do, though, is to go over those kinematics equations one more time. So once again, these are the kinematic equations in the order that I gave them to you in class. And so let's just review. We have df, or final displacement, equals di, initial displacement, plus your velocity times time. We have vf, final velocity, equals vi, initial velocity, plus a times t, acceleration, times time. We have delta d, or your displacement, equals your initial velocity times time, plus 1/2 the acceleration times time squared. And then vf squared equals vi squared plus 2a delta d. Now, as we talked about in class, we're going to talk about the times that you should use these equations. So how do you know when to use them? Now, first off, this first equation only works when you have a constant velocity. If it's accelerating or the velocity changes, then you can't use that equation. Now, what you have to do is look at the equations and see which variable is not in the equation, because that means that's how you decide which one you're going to use. The second equation does not have displacement. So if the question does not say anything about displacement or does not give you displacement, then you would use this equation. This third equation, it does not have final velocity. So anytime you have a problem where you do not have the final velocity, or you don't ask for the final velocity, you don't need the final velocity, then you can use this equation. And then, of course, this last equation we use whenever there is no time, because this is the only equation that does not have time in it. So if the question doesn't give you time, then you can use this equation to solve for the other variables. Okay, so now that we've briefly gone over that, let's talk about the first example problem and work it out. So this problem tells us a golf ball is at rest on a tee before it is accelerated to a velocity of 55.56 meters per second in 5.6 times 10 to the minus 4 seconds. What is the golf ball's acceleration? So the first thing we want to do is look at the stuff that gives us in the question. And we know that it is at rest and that it is accelerated to a velocity of 5.56 meters per second, and that happens in 5.6 times 10 to the minus 4 seconds. So what I'm going to start off by doing is writing out what I have. The ball is at rest. That means that the velocity initially, and let me erase that because I meant to use my pen. The velocity, if it's at rest, the initial velocity is 0. And if it's accelerated, we know that there is an acceleration. We don't know what that acceleration is, though, and that, of course, is what the question is asking us for. And that's in meters per second because it's a velocity. Now, it goes to a final velocity of 55.56 meters per second. And it does that in a time of 5.6 times 10 to the minus 4th seconds. So after I write down everything from the question, I then need to write down the equation. Now this equation, I have VI, I have VF, I have A, I have T. The thing that this problem does not ask about, does not talk about, is displacement. So I'm going to use the equation that does not have displacement in it. VF equals VI plus AT. And then, of course, I need to solve this equation for my acceleration because that's what the question's asking for. So to solve for acceleration, I'm going to first subtract my VI from both sides. So that gives me VI minus VI on both sides. And that's going to give me VF minus VI equals AT. And then, of course, I'm going to need to divide by T on both sides so that I can get my final equation of A equals VF minus VI divided by T. So then if I plug in my numbers, my acceleration is 55.56, or my VF, minus 0 divided by my time of 5.6 times 10 to the minus 4th. And when I put that in my calculator, I will get an answer of my acceleration of 99,214 meters per second squared. So there is my first example of working out the problem. And I want you to notice that we wrote down all the information we were given and what we were asked for in the question. Then we write down our equation, then we algebraically solve the equation, and then we plug in our numbers and get our answer. And that's the best, fastest, easiest way to solve any of these problems. So let's look on at example, or part B of this example. So we'll go ahead and clear all of this off and then start with the next part. So this is the same golf ball, same situation, except this time we want to know how far did it travel. So right now it's wanting to know delta D. So I'm going to use delta D, and I have all of the same given information, so I don't need to write it down again because I just did it. Hopefully you still have that written down in your notes. But I do need to pick my equation. Well, this time I know my final velocity, I know my initial velocity, I know my time, and we just calculated our acceleration to be 99,214. So, and that's in meters per second squared. So I know A, I know T, I know VI, I know VF. The only thing I don't know is my displacement. So I'm going to use the equation that has delta D equals VI times T plus 1/2 AT squared. And that's already solved for what I'm looking for. Since my VI is 0 because it starts at rest, 0 times T is 0, so that whole term disappears, and I have just delta D equals 1/2 AT squared. So now if I plug in my numbers, that's going to be 1/2 times my acceleration of 99,214 times my time of 5.6 times 10 to the minus 4th, and plug that into my calculator, and I get an answer of delta D equaling 0.015 meters. So it's a very short distance, but I'm going from a rest, or 0, to very fast speed in an extremely short amount of time. So I'm going to end up moving for a very short distance with an extremely large acceleration. Okay, so let's clear this and start with the next problem. So this problem, once again, we're going to write down all of our given information first. So when a flea flies off the ground, it has an acceleration of 2.0 times 10 to the third. So my acceleration is 2.0 times 10 to the third meters per second squared. The flea reaches a height of 3.6 times 10 to the minus 2 meters. Well, that's in meters, so that's a displacement, and it is 3.6 times 10 to the minus 12, not 12, minus 2 meters. Now, the question doesn't actually give us anything else, but I want to know the flea's velocity. That's what the question's asking for. So I'm obviously wanting to know his final velocity when he reaches the top. So we can assume that his initial velocity, since he is accelerating, we know that the velocity is changing. We know it's not the same as the final velocity, so it's not a constant velocity situation. And since I didn't tell you what the velocity is, we're going to assume its starting velocity is 0. And you can pretty much do that on any problem I give you. If I don't tell you the initial condition, then you can assume the initial condition is 0. So with this question, the one thing I do not have that I need to know, or would normally need to know, is the time. So if I don't know time, there's only one equation I can use. Vf squared equals Vi squared plus 2a delta d. So now I would like to solve this equation for Vf, which is very simple because, well, I have Vf on the left already, but it's squared. So I simply take the square root of this entire side, and I take the square root of that side, and that gives me an equation of Vf equals Vi squared plus 2a delta d square root. Now, once again, since my Vi is 0, then this Vi is still 0, and 0 squared is 0, so that term disappears, and I don't need it. And so I simply plug in, and I have the square root of 2 times a, which is 2 times 10 to the third, times delta d, which is 3.6 times 10 to the minus 2. Extend that square root over that, close off the parentheses. That's going to give me my Vf, and when I put all of this in my calculator, I get a final velocity of 12 meters per second. So that is my final answer, and let's make sure we know what our final answer is by putting it in the box. Alright, so there's a second part to this problem as well. So let's clear this off and we will continue on with that problem. Okay, so it's the same situation. We have the same acceleration, the same displacement. The V naught, or Vi, is 0 still. This time I want to know how much time has passed. Now the interesting thing here is that there are two different equations we could use. We could use the equation of Vf equals Vi plus At, because we know Vf, we know Vi, we know A, and we know T, and we could solve for T that way. We can also use the delta D equals VIT plus 1/2 AT squared. Either one of these equations would work, but I personally would say that this is a better choice. And the reason that this is a better choice than this one is because whenever I eliminate my Vi because it's 0, and I have delta D plus 1/2 AT squared, if I'm solving for my time, then I need to know time, so I would do the algebra. Well, the acceleration was given to me in the problem. The displacement was given to me in the problem. I think this is a better choice because if our answer to number or part 1 was wrong, if my final velocity is wrong, and I use that wrong final velocity here, then I will get a wrong answer there. So I'm going to use this equation because I'm only using numbers that were given to us, not a number that I had previously calculated. So to solve this equation for time, the first thing I need to do is I need an equal sign there, not a plus sign. And then the first thing I need to do is multiply both sides by 2. That gets rid of the half on this side because 1/2 times 2 is 1. So that gets rid of that, and it leaves me with 2 delta D equals AT squared. I then divide both sides by A so that my A's will cancel over here. and that gives me t squared, and so then I'm going to need to take the square root of both sides, which would give me a final answer of t equals the square root of 2 delta d over a. Then if I plug in my numbers, which I ran out of room here, so I'm not going to write that on there, but if I plug in my numbers, I get an answer of t equals 0.006 seconds. So it happens very, very quickly, and that is, of course, my answer. So hopefully these examples made sense to you, and I hope that you have a wonderful evening as you go about your looking at solving more kinematics problems. So this is the end, and I hope you have a wonderful day. Bye-bye.